cat is held upside down, about 2 feet off the ground, belly to the ceiling. Just an ordinary house cat, hanging there in someone's hands, not a worry in the world. Now somebody lets go. The cat falls. It lands on its feet. That is the whole story. And there is nothing in that story that should bother you, because you have seen it your entire life. Cats land on their feet. Everybody knows it. We have proverbs about it. We have sayings about it. It is one of those facts, so ordinary, that nobody thinks to ask whether it makes any sense. But it doesn't. It doesn't make any sense at all. Take a screwdriver and drop it. The screwdriver lands however it lands. Drop a teacup, the teacup lands however it lands. Drop a rock, and the rock just falls. Whichever side was up stays up, more or less. Whichever side was down hits the ground. Falling things do not choose how to land. A cat chooses. A cat starts upside down, perfectly still. No push, no spin, just held there like a sack of potatoes. And in the half second it takes to fall, the cat manages to flip over and land on all 4 paws. Quietly, like nothing happened. I want you to think about that for a moment, because I am about to tell you a secret. There is a law of physics, a serious one of the deepest laws we have, that says the cat cannot do this. It cannot. We have known this law for over 300 years. Newton wrote it down. We have tested it 10,000 ways, and it always works. It works for planets and for billiard balls and for spinning tops and for the whole solar system. And yet the cat is doing it, right in front of us, every single time. So either Newton was wrong, and let me tell you, Newton was not wrong about this, or there is something going on inside that cat that we are not seeing. I want to tell you what it is, but not yet. First, I want to tell you about a Frenchman with a camera. His name was Étienne-Jules Marey. He worked in Paris in the 1890s, and he was obsessed with motion. Not motion in the abstract sense, the way a mathematician would talk about it, but motion as a real physical thing happening right in front of his eyes. He wanted to see it. The trouble was, most motion happens too fast for the human eye. A bird's wing in flight, a horse's gallop, a whip cracking through the air. They all blur. Your retina just smears them together. Marey built the cameras to slow these things down. He arranged strips of film and rotating shutters, and he caught 12, 20, 60 pictures a second, all in a row, frozen on the plate. For the first time in human history, you could look at a moment and stop it cold and study it. In 1894, he pointed his camera at a cat. This is a story I am not making up. He really did this. He held a cat upside down in front of a white background. He dropped it from about 1.5 meters. His camera caught the entire fall, frame by frame. And when the photographs came out, the people who looked at them did not say, "Oh, what a charming sequence." They said something closer to, "Wait a moment, that is impossible." Because the photographs showed a cat rotating itself in midair, without anything to push against, without anything to grab onto. The cat just twisted. And every physicist who looked at those photographs had the same uncomfortable thought. This cannot be right. Let me tell you why. There is a law called conservation of angular momentum. Don't be scared by the name. Angular momentum is a fancy word for spin. If something is spinning, it has angular momentum. If something is not spinning, it doesn't. Here is the rule. If a thing has 0 spin and nothing twists it from outside, it cannot start spinning by itself. You can shove it, throw it, wave it around. None of that gives it spin. The only way to put spin into a thing is to twist it from the outside. You want to test this? Sit on one of those swivel chairs, the kind that rotates freely. Sit perfectly still. Do not touch the floor with your feet. Do not push off anything. Now try to spin the chair, just by wiggling. Try waving your arms around. Try throwing your weight from side to side. Try yelling at it. You will get nowhere. You will jiggle. You will lurch. The chair will not turn. That is not me being mean. That is the universe being strict. Newton said it. The universe agrees, and there are no exceptions. Without an outside torque, your spin is locked. Now consider the cat. The cat is held in someone's hands. Belly up, not spinning. Zero spin. The hands let go. The cat is now in free fall. And in free fall, gravity acts on every part of the cat equally. Gravity does not twist anything. Gravity just pulls. So during the fall, no one is twisting the cat. No outside torque. None at all. By the rule I just told you, the cat must keep its spin at zero. Forever. Or at least until it hits the floor. But the cat rotates 180 degrees and lands on its feet. So either the law is wrong, or the cat has zero spin and a 180-degree rotation at the same time, which sure sounds like a contradiction. This is what Marey's photographs gave the world. A real, hard, you can see it with your eyes contradiction. A cat doing what physics says cats cannot do. So what do we do with this? We have two choices. Either we throw out a law of physics that has worked for 300 years and works for every other thing in the universe, or we figure out what the cat is doing that we have not yet noticed. Just so we keep moving, I will spoil it a little. We do not throw out the law. The law is fine. The cat is fine. But to see how, we have to look very, very carefully at what a cat actually is. Let me start eliminating suspects. Suspect number one. Maybe the cat is pushing off the air. Maybe it is like swimming. The cat moves its paws, the air pushes back, and that is how it spins. This is a reasonable guess. Lots of smart people guessed it. So let us check. Air is thin. Cats are dense, by comparison. When you swim, you are in water, which is about 1,000 times denser than air. A cat trying to swim against air would get almost nothing. The forces are too small. The fall is too short. The whole event is over in about half a second. But more importantly, we can test it. We can drop something cat-shaped in a place with very thin air, or no air at all, and see what happens. People have done equivalent experiments with mechanical models, with humans on trampolines, with astronauts inside spacecraft in zero gravity. And the answer comes back the same. The flip works without air. So air is not the trick. The cat is not swimming. Suspect number two. The tail. Cats have tails. The tail is heavy and flexible. Maybe the tail acts like a counterweight. Whip the tail one way, the body goes the other way. Also a reasonable guess. The tail does help, a little, but here is the trouble. There is a breed of cat called the Manx. Manx cats have no tail, or barely any, and Manx cats land on their feet just fine. So the tail is not doing the heavy lifting. It might be helping a bit. It is not the answer. Suspect number three, just to clear it off the table. Maybe the cat hangs on to something, magnets, static electricity, some hidden physics. No. People have done this experiment 1,000 times in clean conditions. There is nothing for the cat to hang on to. The cat is in the air. Period. Now we have a problem. We have eliminated the easy suspects. Air does not do it. The tail does not do it. The cat is in mid-air, there is no floor to push off. What is left? What is left is the cat itself. Just the cat. Just the cat's body, in the air, doing something. And whatever the cat is doing, it has to obey the law. The cat starts with zero angular momentum. It must end with zero angular momentum. Newton is not making exceptions for furry little animals. So whatever rotation the cat performs, in some careful mathematical sense, the angular momentum must add up to zero. I want you to look at Marey's photographs again, in your mind, or imagine them. 60 pictures of a cat falling, frame by frame. Most people, when they look at those pictures, see a cat rotating like a corkscrew, like a single object, a stiff stick, twisting around its long axis as a whole. But if you look more carefully, and physicists started looking more carefully in the early 1900s, and even more carefully in the 1960s, and they are still looking, you see something different. You see the cat changing shape. The front of the cat is doing one thing. The back of the cat is doing another thing. The cat is bending in the middle. The legs tuck in and stretch out. The whole animal is squirming, not turning. That is the clue. The cat is not a rigid body. The cat is a deformable body. You might say, well, so what? The cat changes shape. So does a piece of dough. So does a wet rag in the wind. That doesn't change anything about angular momentum. But it does. It changes everything. Let me tell you about figure skaters. You have probably seen this. A figure skater spins on the ice. Arms out. Slow spin. Then she pulls her arms in close to her body, and suddenly she is spinning much faster. Then she pushes the arms back out, and she slows down again. Why? Angular momentum is conserved. That same law again. So when she pulls her arms in, she becomes more compact, and to keep her angular momentum at the same value, she has to spin faster. When she sticks her arms back out, she becomes more spread out, and she spins slower. That is a real thing. That is not magic. That is the law working. But notice something. The skater starts with some spin, some non-zero amount. She is using shape changes to redistribute that spin between fast and slow. She is not creating spin out of nothing. She had spin to begin with. The cat has no spin to begin with. So you might think, all right, the skater trick does not apply to the cat. Different problem. You would be partly right. The cat is not doing the skater trick, but the cat is doing something that uses the same fundamental idea, that shape matters, in a much sneakier way. Let me ask you a question. If you have a thing that can change its shape, and the thing has zero angular momentum, can it still rotate? Can it end up oriented differently from where it started, without ever having any spin at any moment in the process? Most people, when you ask them this, say no. They say if you have zero spin the whole time, you cannot rotate. Spin and rotation are the same thing. But they are not. Spin is angular momentum. Rotation is a change in orientation. These two things sound like the same thing. For a rigid body, they are the same thing. For a brick, or a screwdriver, or a billiard ball, no spin means no rotation. They are locked together. For a deformable body, for something that can squish and stretch and reorganize itself, they come apart. You can have rotation without spin. I know that sounds crazy. Let me show you what I mean. Imagine a person sitting on a swivel chair, stationary, arms straight out to the sides, holding heavy weights in each hand. The chair spins freely. The person has zero spin. Now the person performs a maneuver. They pull their right hand in close to their chest. They push their left hand way out. Then they swing their upper body around, like reaching for something behind them. Then they push the right hand back out and pull the left hand in. Then they swing the upper body back toward the front. If you do this just right, and people have done it, and we have movies of it, the chair will be facing a different direction at the end than it was at the start. Not by much. But really and truly, the person has rotated. The chair has rotated. And during the entire maneuver, the angular momentum was zero. Newton's law was never violated. Not for a single millisecond. How? Because rotating is not the same thing as spinning when you can change your shape. Here is how to think about it. The person has two arms. The arms can be at different distances from the body. Pulling an arm in close means that arm is easy to swing. It has a small moment of inertia, we say. Sticking an arm out means that arm is hard to swing. It has a big moment of inertia. Imagine the person twists the upper body to the right. They have to twist against something. They twist against the lower body, which is sitting on the chair. Whichever way the upper body goes, the lower body has to go the opposite way, because the total spin must stay at zero. That is Newton. If the upper body has a big moment of inertia, and the lower body has a small one, the upper body twists a tiny bit, and the lower body twists a lot. If it is the other way around, the upper twists a lot, and the lower twists a tiny bit. Here is the trick. The person changes shape between twists. They twist one way with arms out, upper body rotates a little, lower body rotates a lot. Then they pull the arms in and untwist the other way, Upper body rotates a lot, lower body rotates a little. When you add up the lower body's rotation across both twists, it does not cancel. One twist was big, the other was small. There is a leftover. That leftover is the rotation. That is the trick. That is the whole trick. You twist one way under one shape. You untwist under a different shape. The untwist does not cancel the twist because the moments of inertia are different. The body ends up rotated, even though it never had any spin. That is what the cat is doing. Let me say it again, because it took physicists a long time to see this clearly, and I do not want to whip past it. The cat is in the air. Belly up. It tucks its front legs in tight against its body, so the front of the cat is now compact. Small moment of inertia. It stretches its back legs out away from its body, so the back of the cat is now spread out. Large moment of inertia. The cat twists in the middle. The front rotates one way. The back rotates the other way. Because the front is small and easy to spin, and the back is big and hard to spin, the front rotates by a lot and the back rotates by a little. Total angular momentum, still zero. Then the cat reverses. It stretches the front legs out. Big moment of inertia in front now, and tucks the back legs in. Small moment of inertia in the back. And it untwists. The front rotates back the other way, but only by a little, because now the front is big. The back rotates back the other way by a lot, because now the back is small. Add it all up. The front of the cat ends up rotated by a lot, minus a little. The back ends up rotated by a little, minus a lot, which is the same a lot rotation in the same direction. Here is the elegant part. The a lot of the front and the a lot of the back are both in the direction the cat needs. The direction that turns belly up into belly down. Net result. The whole cat has rotated about 180 degrees, and the total angular momentum throughout the entire maneuver was exactly zero. Newton is happy. The cat is happy. The cat is on its feet. This is not the kind of thing you would guess sitting in your armchair. It took the photographs of Marey to show that something was happening. It took a few decades to start to understand what, and the full mathematical story did not really get sorted out until the 1960s, when two engineers wrote down a careful model of a cat as two cylinders joined at a flexible spine, and showed exactly how the maneuver works. But there is something deeper here, and I want to tell you about it, because this is where the cat stops being a story about cats and starts being a story about geometry. When you and I rotate, in a normal way, when I turn my whole body around to look behind me, I am applying a torque. Something is twisting me. My feet push on the ground. The ground pushes back. There is a force. There is spin during the turn, and the spin gets cancelled at the end when I stop. When the cat rotates, there is no torque, no force from outside, no spin at any moment. The cat rotates by going through a sequence of shapes and coming back to the original shape, but in a different orientation. Think about that. The cat starts as cat shape. It goes through tucked front, extended back, then twisted, then extended front, tucked back, then untwisted. And then the cat is cat shape again. The same shape, identical, but pointing a different way. In a sense, the cat has made a closed loop in shape space. It started at a point in that abstract space, traveled around and came back to the same point. But in real space, in physical space, the cat is now oriented differently. That, friends, is a deep idea. It has a name. Mathematicians call it holonomy. It shows up all over physics. It shows up in why a Foucault pendulum precesses. It shows up in quantum mechanics, in something called the Marey phase. It shows up in general relativity, in the way light bends around the sun. The basic idea is always the same. You travel through some space. Could be shape space, could be quantum state space, could be ordinary curved space. You come back to where you started. But where you started turns out not to mean exactly the same thing as before. The journey itself rotated something, without forces, without torques, just by going around. The cat is doing geometry, not the geometry you learn in school, with triangles and circles. A different kind, the geometry of curved spaces, where moving in a closed loop changes you. I want to give you a simple version of this idea, because it is genuinely beautiful and I do not want it to feel mystical. Imagine you are standing at the North Pole, holding a stick. The stick is pointing in some direction. Let us say it is pointing toward Africa. Now you walk south, keeping the stick pointing the same direction the whole time. You are not turning the stick. You are just walking, and parallel transporting the stick along with you. You walk all the way down to the equator. The stick is still pointing toward Africa. Good. Now you walk along the equator, a quarter of the way around the world. You are not turning the stick. You are just walking. The stick is still pointing the same direction it was, locally, the whole time. Now you walk back up to the North Pole. Here is the strange thing. When you get back to the North Pole, the stick is not pointing toward Africa anymore. It is pointing somewhere else, maybe South America. The stick has rotated, even though you never turned it. The rotation came from the curvature of the Earth, from walking around in a closed loop on a curved surface. That is holonomy. The cat is doing the same thing, but in a different kind of curved space, the curved space of all possible cat shapes. Walking around in that space rotates the cat in real space. I want to be careful here. You might walk away from this thinking the cat has somehow figured all of this out. The cat has not figured anything out. The cat is doing what cats do. It is twisting and tucking, and millions of years of evolution have shaped its instincts so that the twisting and tucking are exactly the right kind to land on its feet. The cat does not know about moments of inertia. The cat does not know about holonomy. The cat is a cat. But the universe knows. The universe is set up in such a way that this trick is possible. A deformable body can rotate without spin. Shape changes can produce orientation changes. The cat is exploiting a feature of physical law, and the cat does not even know it is exploiting anything. Evolution found the trick by trial and error, and now every kitten is born already knowing it. They come out of the womb pre-programmed with a piece of geometry they will never be aware of. I find something beautiful about this, and let me try to put my finger on it. When you first hear the puzzle, cat falls, no spin, lands on feet, you think there must be something wrong. Some hidden trick, some violation of physics, some mistake. And the physicist's first instinct is to say, well, there is no mistake. The laws are sound. The cat must be cheating somehow. But it is not cheating. It is doing something subtle and exact and consistent with every law we know. And the more you look at it, the more you realize the laws of physics are richer than they looked at first glance. They allow for things you would not have thought possible. They have deep structure. There is a kind of generosity in them. They say, yes, you can rotate without spinning, if you are clever about your shape. They open doors you did not know were there. That is the joy of physics, for me. Not that it tells you no, you cannot do that, but that it tells you, well, maybe you can, but only in this particular way, and let me show you why. There is a question I want to come back to, because I left it hanging earlier. I asked, can a thing have rotation without spin? I said yes, if it can change shape, but I want to refine that answer, because there is something else interesting about the relationship between shape changes and rotation. If you change your shape and then go back to the original shape, you do not necessarily come back to your original orientation. We saw that with the cat. The cat ends up rotated. But what if you do the shape changes in a different order? Or in reverse? Here is a fun one. If the cat could play the whole maneuver backwards, extend the front legs first, tuck the back legs, twist the wrong way, then tuck the front, extend the back, untwist, what would happen? The cat would end up rotated in the opposite direction. It would unflip. This means the rotation depends on the path through shape space, not just on the start and end points. On the route taken between them, that is a strange property. In ordinary geometry, paths do not matter for things like total displacement. If you walk 100 meters north, you have gone 100 meters north, no matter how you wiggled along the way. The path does not matter, only the endpoints do. But for the cat's rotation, the path matters. Two different paths through shape space, both starting and ending at cat shape, can give two different final orientations. One of them might give 0 rotation, another might give a 180-degree flip, a third might give 30 degrees. This is what holonomy means in technical terms. Path dependence, in a context where you might naively expect path independence. When physicists realized that the cat's trick worked this way, in the 1960s and the 1970s, they started seeing the same structure everywhere. The same path-dependent rotation, the same geometric phase. It became one of the unifying ideas of late 20th century physics. You see it in the behavior of crystals, in the rotation of light through certain media, in the response of quantum systems to slowly changing fields. The cat is, in a strange way, an ambassador for a whole branch of mathematics. Robotic engineers got excited about this, because if you could understand the cat's maneuver mathematically, you could build robots that maneuver in space without rocket fuel, just by changing shape. Astronauts use a version of it. They swim through the air in 0 gravity by carefully chosen body motions, and the math behind it is the same falling cat math. Astronauts in the early space program had to learn to swim without water. They had to learn that to turn around in 0 gravity, you cannot just push off something, because there is nothing to push off. You have to twist your body in a careful way, like a cat, and let geometry do the work. The first astronauts had a hard time with this. Their bodies wanted to do the everyday life motions, the motions that work when you have a floor to push against. The motions that work in 0 gravity are different. They look weird. They look like cat motions. There is a quite practical use, too. Spacecraft attitude control. If you have a satellite tumbling in orbit and your thrusters fail, can you stop it from tumbling using only internal moving parts? Wheels, gimbals, whatever you have inside. The answer is yes, in principle. And the math is the falling cat math. You change the spacecraft's shape by spinning internal flywheels, and you can rotate the whole thing without expelling any fuel. We use this all the time on real spacecraft. So the cat, dropped from 1.5 meters, twisting in midair, is doing the same thing as a billion-dollar spacecraft 1,000 miles up. The cat figured it out first. The cat had a head start of about 100 million years. I find this delightful. We humans, with our clever brains and our equations and our high-speed cameras, took until the 1960s to write down a clean theory of the falling cat. The cat had been doing it the whole time, calmly, without a single equation, without any concept of shape space or moment of inertia or angular momentum. The cat just falls and lands on its feet, the way a leaf falls down or a stream runs downhill. It is just what cats do. That is the punchline I keep coming back to in physics. The world was here before we were. The world has always been doing whatever it does. We come along and we look, and we are confused, and we make up stories, and we test the stories against the world, and slowly we find better stories. The world does not care which stories we tell. The world just keeps doing its thing. The cat keeps landing on its feet, whether or not we understand it. But there is a special pleasure when we do understand it, when we see finally what the cat has been doing all along. When the contradiction disappears, not because we threw out a law, but because we found a richer interpretation that contains both the law and the puzzle inside of it. That is when physics is most fun, not when you discover a mystery. Any fool can discover a mystery. But when you discover that the mystery was not really a mystery, it was a feature of the world that you simply had not noticed yet. Let me close with one more thought. I told you the cat performs a specific maneuver. Tucks front, extends back, twists, switches, untwists. That is the version those engineers worked out in the 1960s. It is a clean model. It is mostly right. But cats are messier than that. If you watch real cats, and people have watched real cats, frame by frame with cameras 1,000 times faster than Marey's, you find that cats use multiple strategies. Different cats do it different ways. The same cat may do it differently depending on how it was held and how high it falls. The tail, when the cat has one, contributes a little. The bending of the spine contributes a lot. The cat may rotate the front and back at different speeds. There are corrections, refinements, subtleties that we have not fully captured. In other words, the cat, even now, is teaching us things. There are physics papers being written about this still. There are robots being designed that try to mimic what cats do. The cat is, in the most literal sense, an open research problem. A small, furry, purring, sleeping research problem. I think that is wonderful. I think most physics is like that. People imagine physics as a bunch of finished, polished laws sitting in a textbook, with nothing left to do but memorize them. That is not what physics is. Physics is what happens when you look at a cat and say, wait a minute, that should not be possible. And then you go and figure out why it is possible. The answer is always more interesting than the question. It always opens up something new. The cat gets to land on its feet. We get to learn about geometric phases and gauge theory and holonomy. Everybody wins. Except maybe the cat, which is now standing on the floor wondering why this person keeps dropping it and writing things down. So the next time you see a cat, sleeping in a windowsill, walking across a kitchen, dropping silently from a fence, remember that there is a piece of mathematics inside that cat. A piece so subtle that we did not know it existed for most of human history. A piece that connects to satellites and spacecraft, and quantum mechanics and curved spaces. A piece that the cat is using right now, every time it jumps off a chair without a thought in its head. The world is full of this. Tricks the universe allows that we have not noticed yet. Patterns in the laws that look like loopholes and turn out to be deep features. Things that seem like they should not work, and yet they work, and they teach us something when we figure out why. That is why I keep poking at the world. Because every time I think I have understood something, the world shows me a cat, and I have to start over. So tell me, what is another everyday thing that probably violates a law of physics? Until you look closely.